So I'm just displaying the slides of last class. You can go through them for revision. Shall we start? Sanjay?
Yes, sir, we can start, sir.
Okay. So we were talking about classification using method of characteristics. I told you the first equation shown here is the full potential equation for compressible flows, and dou phi by dou x is u, dou phi by dou y is v, and all that stuff. The second one is the expression for du on the right hand side. Dou e by dou x into dx plus dou e by dou y into dy. Sorry, dou e by dou x, yeah, dou e by dou y into dy. So dou e by dou into dy is written as u is written as dou phi by dou x here. So it will make meaning. The third one is expression for dv. Similarly, you'll have dou phi by dou y as v. So dou v by dou x into dx plus dou v by dou y into dy is what expressed in the third equation. So as told earlier, we have a matrix into phi xx, phi xy, phi yy, which is the second matrix. So the is equal to the right hand side 0 du dv. If you want to solve the system of equations, you want to say one variable phi of xy, you will get this by Kramer's rule. So Kramer's rule says that whatever matrix you get, okay, it's the denominator. This matrix is a matrix on the left hand side into phi xx, phi xy, and phi yy, yeah. So when you solve for phi xy, the middle term coefficient of phi xy is replaced by the right hand side 0 du and dv. Okay, here it is this minus 3y squared, then here dy, and then here it is dx. So instead of dy you put du, instead of dx you put dv, instead of this one you put 0 in the same matrix. That is the numerator here. Okay, so now what is this? This is actually you can call this as dou u by dou y or dou v by dou x. Both are phi x for rotational field. Now we are defining the characteristic lines, a set of imaginary lines in solution space for a PDE. Along this line, flow variables are continuous, but the derivatives are discontinuous. If you want me to be more specific, I will say the derivatives are allowed to be discontinuous. Okay. Now, if you want to find these lines, all you have to do is set the denominator here 0. If you set the denominator 0, then that is the denominator is nothing but definition of a characteristic line. If denominator is 0, that means that there is a condition for a characteristic to exist. So that will give you this. You rearrange, you get in a space in which fluid is flowing with velocities components uv, which also has a speed of sound a. At any point, you take some direction dy by dx. Okay. Now, if it is a characteristic direction given by the right hand side, if the dy by dx is given by the right hand side, that is the characteristic direction at that point. Okay, I think I can illustrate with a figure. There are many points in space, let's say, okay. At every point, you have, for this point, for example, you call this point, you'll have u, v, a. So substitute the values of u, v, and a at this point, the right hand side. And if that expression dy by dx is given by the right hand side, you take, it is nothing but a direction. For example, at this point, it may be this direction. Okay, dy by dx may be equal to something. So if it is a negative number and you draw this will be a direction of characteristic at that point. When you come to this point, the direction may not be the same. It may be something like this. Okay, at this point. At this point, it may be something like this. At this point, it may be something like this. At this point, again, it may be something like this. Okay, and so on and so forth. So at every point, the direction of this dy by dx is given by this right hand side here. So we say if you join points are very close together. Let's assume few points very close together. You draw some line, you follow there, you come to some other point. At that point, again dy by dx may be different. You draw a straight line. At a very small near point, another may be different, So this line, when you join them by straight lines, approximate straight lines, this line you call as characteristic line in space, 2D space. Okay. Characteristic curve or line. So you define at a point. If you want to see a curve, then it's defining at many points, very adjacent points. In the limit, when these points are, very close to each other, then instead of these, all these straight lines will appear like a smooth curve. That's a characteristic curve. If there are any doubts, please, you stop me in between. Now let's look at more at the behavior of this. If you look at the right hand side, there is the square root. U squared plus v squared is nothing but the total velocity squared divided by speed of sound squared. Velocity by speed of sound is Mach number. So this term is m squared. M squared minus 1. Square root of m squared minus 1. That is the discriminant. Okay. Remember that when you set the denominator to 0 here, you'll get two solutions, plus or minus. You take a square root, you can have a plus root or minus root. Okay. So you will finally realize that two possible directions are there for this dy by dx. So at a point, it is not only one direction, but there are two directions. So what it says is there can be two directions. In a particular point, we saw only derivatives like this, but there may be another direction like this. Okay. So whether you proceed in this manner or this manner, you will be moving along a characteristic line or characteristic direction. So now discriminant is positive. What happens? You'll have real roots. If discriminant is 0, you'll have only one root. If discriminant is negative, you'll have imaginary roots, which means these characteristics will not exist. If we have imaginary roots, that means there is no solution, which means the characteristic lines don't exist. So look at the sign of m. M squared minus 1 is what is inside the root. If m is less than 1, what happens? M squared is less than 1. M squared minus 1 is negative. Square root of a negative number is not real, right? So we say no solutions exist for this dx. In other words, it means for subsonic flow, when Mach number is less than 1, we have subsonic flow, there are no characteristics. There are no real characteristics, and there are no characteristics at all. So the concept of characteristic does not have a meaning in subsonic flow. When the flow is sonic, that is m is equal to 1, the term inside square root becomes 0, so you get only one root. There is only one direction along which this is valid. Okay, so there can be two directions, but in that case, there is only one direction. In that case, we call the equation as parabolic. When Mach number is less than 1, it is elliptic, where there are no characteristics exist. When Mach number is equal to 1, only one root is there for the equation, so only one characteristic is there. Characteristic direction is there. If Mach number is more than 1, then the discriminant is positive. So plus or minus positive number, you get two roots. So there are two characteristics. For the hyper, we call the equation the hyperbolic equation. Okay. Any doubts in this? No doubts. Shashank, any doubt?
No, sir.
Okay. So don't worry about this other classification. So you can go through, but not it's just out of place here. It is same as b squared minus 4ac. That will be good enough. One more method of classifying. Okay. Very general method. Now you have this is what I was telling now. There are no characteristics. Let me go to the slide show. There are no characteristics for this system. Above me, this system. If Mach number is subsonic, m is less than 1, so this case is PDE is elliptic. Where do you encounter this elliptic problems? One is in inviscid irrotational compressible flow, where flow is subsonic. That's the first point. Or if you have equilibrium problems in closed domains. For example, you have some problem like this. Okay. You have some box, closed domain, okay, all wall, solid wall. there's a small blast here. Wave is propagating, getting reflected, moving somewhere. Okay. In all directions, there's some blast. The wave propagation. Okay. In closed domain. You only know there's a solid wall there. So what is the fluid motion after that? This is a closed domain problem. Such problems are elliptic. That's what is meant here. Elliptic PDEs govern equilibrium problems in closed domains, which means that not unsteady. It's not an unsteady problem. You want to know when time tends to infinity, what is the effect of this? For example, heat is generated from here. After infinite time, what will be the heat here? So in between, it may go through a process. We are not bothered with the process. Final equilibrium condition, you need to find it. So such problems tend to be elliptic problems. Then Mach number is 1. We have in fluid mechanics, the PD is parabolic. Only one characteristic is there. So this parabolic PD is govern propagation problems in open domains. See, instead of telling one characteristic, we are telling where real repeated characteristics exist. Another way of telling there is only one characteristic. There's one. In general, there are two. If the two become one, you say that the characteristic repeats itself, which means there is only one character. Okay, just English play. So suppose this same heat you just you have a surface from which heat is generated and it is propagating. Okay, it is propagating along this open domain here. When the domain is open, you tend to get parabolic problems. Now, two characteristics: when Mach number is supersonic, the equation is hyperbolic. Hyperbolic TEP is given propagation problems in open domains where real distinct characteristics. So, this kind of open domain problem can have both parabolic and hyperbolic nature. Any doubts so far? So I assume that everything is crystal clear to all of you. Now we'll look at what is called as the well-posedness of problems. Problems which are well-posed. Okay. Before we do that, we'll take a small break. Because of this monotony, I'm feeling sleepy myself. So we need to take a break. Now, Yuvraj.
Yeah, I'm here, sir.
Yeah. Can you share something with us?
Something.
Something, whatever you feel like.
What else? I know we don't feel like anything, but like not sure what to say. Sir.
No, just tell what you like to do, your hobbies.
So, and then this final year seems to be quite overloaded for me because the college works is issues because that is something that is so important. But apart from that, I have been working in a service organization, and as this will be my final year for my career to pursue my career, I have to leave the service organization and I may have to move city. So this year I feel that I have to make things right, and so that my organization won't feel my absence as a thing. So yeah, so I have put in. I'm actually putting more effort in that one, sir. So
Yes,
in
yes,
that
it's a
way,
very important, very
yeah,
important year for you.
yeah,
Correct. Yeah.
yes.
Yeah,
So
continue.
yeah, so we are trying to, we are the organization like started like
Balancing a lot of
with
things. Balancing a lot of
yes,
things. Yeah,
most of
just
them
like
are at my age, and everyone have to see their career. So we all are
uh,
kind of putting our efforts to
what
give
service
it to
does
the
the
next set of
organization?
people.
Yeah. What does the
I hope you
organization do?
know the road track. Road
Yeah, yeah,
track.
yeah. Yeah, Road Track. I know Road Track
Yeah.
Club. Yeah.
Yes,
Okay.
sir.
Good.
I'm
Yeah,
a
they
part of
do
it.
a lot of service. Good.
Yeah.
Good.
Good.
Continue the good service. But
So
this year alone, you take you have to work hard because a lot of things will be there. There's no
yes,
escape from that. Project will be there. Aero design will be there. Every subject, the teacher will assume that is the only subject you are studying in your for your whole life. Okay,
yes,
but you have to balance everything. Okay, so
yes,
put more effort in your studies this year. It will give you very good results later.
yes.
Yeah. Okay. Thanks, Yuvraj. Thanks for sharing. We'll get back to the lesson. Hmm? Okay. Now we'll go to the next part. That is, we are talking so much about discretization. So we see, how to discretize these PDEs. We all know this Taylor series very well by now, thanks to the efforts of um, who did Niveta, no? Who did on Taylor series? Niveta. So we know what is the Taylor series now. Discretization of PDEs. So we'll be looking at this. In this chapter, when you discretize the partial differential equations, you call them finite difference equations. Finite difference equations, not differential. It's known as FDEs. So you can imagine a straight line, a curved line being broken into straight lines. There's a certain philosophy in that. You are linearizing that non-linearity piecewise. Every piecewise it is linear. Okay. Similarly, when you have PDEs, we want to linearize the derivatives also. Second derivative, first derivative, nth derivative. We need to make them look linear. Okay, so sum of many linear things can approximate a non-linear behavior. We are trying to same thing by discretization. Partial differential equations are very continuous. They are continuous substances. You are trying to discretize them so that they are manageable. They become linear in a short distance. Then in the next short distance also they are linear. But when you take the sum of this, they can approximate the non-linear behavior. When you take them contiguously, when you arrange them side by side. Okay. We look at the discretization now. So analytical solutions of partial differential equations involve closed form expressions. So for example, y is equal to x squared. At every point, you know x, you know y. You don't have to say that, the value of y at x is equal to 2 is approximately 4. No, it's not approximately 4, it's exactly 4. So the partial differential equations actually give you the exact mathematical representation of the physical problem, or as exact as possible. It is exact. Physically, if you can express it, physically, if you can formulate it and express it mathematically, the mathematics will, which is in the form of PDEs here, it will faithfully represent the physics, whatever with the physical approximations you made. Okay. Now, This involves closed form expressions which give the variation of the dependent variables continuously throughout the domain. By contrast, numerical solutions give answers only at discrete points in the domain. We have seen this. These points are known as grid points. So Sri Krishnan sir may soon start taking classes for you on this, on how to do them. So you will get a practical experience also. CFT, I just am taking a small detour here. CFD is one area in aerospace where you have more job openings. Okay. So if you like this course and if you know the software well, if you know the concepts here very well, you can market yourself as a candidate for CFD engineer positions or entry level positions for CFDs. You can. Meaning there are more openings there than the average aerospace level openings. Okay. So even in the field of mechanical engineering, we have CFD. In chemical engineering, we have CFD. In civil engineering, we have CFD. You can apply CFD to even electronics engineering. You may not believe it, but inside the electronic parts, things get heated up. If you want to predict how to cool them, people use CFD. Okay. And for anything which flows, you can use CFD. So just to stress the importance of CFD, then a typical rectangular grid is shown here. It's very simple, you can see. On X and Y axis are shown. So on the top right, it's not very obvious. Here you can see delta X is the distance between this point and this point. Delta Y is the distance between this point and this point. Now suppose you have one point called I, j, and you have a rectangular grid made only of rectangular points. The points are spaced equally in the x-axis with the distance delta x between them. Then equally on the y-axis also with distance delta y between them. Delta x need not be equal to delta y, so that's why we call it a rectangular. So suppose you have a point I, j. Obviously, you can call the point below that as I, j minus 1. To the right as I plus 1, j. To the top as I, j plus 1. To the left as I minus 1, j. Then these corner points, right? The right bottom corner is I plus 1, j minus 1. The top right is I plus 1, j plus 1. Top left is I minus 1, j plus 1. And bottom left is I minus 1, j minus 1. So just have this firmly in your mind. This picture, just take a photograph in your mind and keep it. Whenever you want, you'll be able to imagine and use this. So discretization is a process where the continuous flow field domain is discretized into a set of discrete grid points. So you want solutions only in these points, which are shown here. So this process is known as grid generation. Second step is discrete the governing PDEs, the governing partial differentials themselves. You have to discretize them and convert them to algebraic finite difference equations in the dependent variables, that is u, v, etc. Now, if you solve this set of PDEs, this will give an approximate solution to the PDE. If you solve this finite differential equation FT, you will get the approximate solution to the governing PDE. That is the aim of CFT. Now, how are these finite differences formed? So we look at forward differencing first. Have you looked at these differences in your FEM course? Niveda? Just hang on for a moment. Hello? Tell me. Okay. So, up to what point did you hear me?
Sir, this forward difference for a moment.
Okay. So far clear? Any doubts? Anyone? Can you assume that there are no doubts? Yes. I'm assuming so. Well, we start with the Taylor series expansion of function u. Okay. And we are looking only at the x direction or I direction. Okay. Where I increases in steps of 1, x increases in steps of delta x. So u at I plus 1 comma j, which means that the value of u, the dependent variable u at the point I plus 1 comma j. So this point, we are talking of the value of u at this point. How is it related to the value at u of I comma j at this point? What is the relationship between these two? So analytically, I can call this as u of x. Here I can call it as u of x plus delta x, which we'll use in the Taylor series. So that's what we are doing here. It is u of I comma j. Imagine it is u of x plus dou e by dou x into delta x. Dou e by dou x at what point I comma j plus dou square u by dou x square at same point I comma j delta x whole square by 2, that is this 2 factorial, plus dou cube u by dou x cube at I comma j into delta x whole cube by 6, this is 3 factorial, and so on and so forth. This is exact actually. If delta x is very small, this will be, very, very close to the exact situation. But delta x cannot be 0. So in reality, there will always be some error. Okay? So if you rearrange this and solve for this term dou u by dou x, so I'll tell you the aim. We want to get an expression for dou u by dou x, approximate expression. That is the first exercise we do. So we take everything else to the, you take dou u by dou x, return it here, taking everything to the other side, and swapping left and right hand side, you will get dou u by dou x is 1 by delta x into u I plus 1 comma j minus u I comma j. Okay, first term by delta x. Then dou squared u by dou x squared delta x whole square 2 by delta x. So it will cancel and you get only delta x by 2 here. Then dou cube u by dou x squared into delta x cube by 6 by delta x. So you'll get delta x squared by 6 here. Okay. So I can say that this dou u by dou x can be approximately written as u at I plus 1 comma j minus u at I comma j by delta x plus, actually you are neglecting all the terms. Let's say you are neglecting all the terms except this term. So you are what is the greatest, the largest term you neglect? It is of the order of delta x. It is some constant into delta x. Now delta x is very small. If it's 0.001, delta x square will be even smaller, 0.00001. Okay. If delta x is not so small, 0.1, delta x square will be 0.01. So we can say the choice of your delta x will affect, and the error you commit will be the order of delta x into some constant. This is called first order method, while the error is of the order of delta x. Okay. So far, if you have doubts, ask right now. Otherwise, we'll go to the next slide.
Excuse me, sir.
Yeah. Who is it?
Sir, Ramnath.
Ramnath. Tell me, Ramnath.
Yes. Sir, in the previous slide, sir, you have mentioned about taking delta x as to be small or bigger, then the result would be. But we don't know about dou square u by dou x square also.
Yes. You're right. So, dou squared u by dou x squared by 2, we assume it is reasonable. It's a reasonable number. Usually, you can prove that if u and v are continuous, dou u by dou x will be of a slightly higher order than dou squared u by dou x squared in general, except you take sine and cos, then you cannot prove this. But if you take some algebraic functions, you can actually say that. But there is no excuse. It is just say that the order of that. So we assume that it is mainly influenced with delta x. Anyway, the dou squared u by dou x squared by 2 term is going to be constant irrespective of delta x you take.
Yes.
It doesn't depend on delta x. So the error depends. We can't control that. But delta x is something we can control. See, order of magnitude is what? Even 10 times delta x, you can say it's same order of magnitude. But 100 times delta x cannot be told in some problems. For some problems, it is 5 or 6 times delta x is same order. But 10 times, 15 times, it's probably higher order. That's what you think.
Yes.
So order means it is not exactly equal to that delta x, if I say it is delta x is 0.01, my error may be in the range of, maybe from 0.002 to 0.1, or maybe 0.015, 0.16. Somewhere there we are taking. Understand?
Yes, sir.
Or even it may be order of 0.05 is order of 0.01, but 0.005 is not the same as 0.01. Then these are not the same order as 0.01.
Yes, sir.
You get the general idea of this order of magnitude analysis.
Yes, sir. I'm getting
You might have done this in your fluid mechanics course, right?
Sir,
You would have,
actually, yes, sir.
yeah.
During
Tell me.
boundary layer.
Bone layer theory, yeah,
Yes, sir.
exactly. So same thing,
Okay.
but you need to get a. It's a good question actually, yeah. But when you say order of magnitude, this is what we mean.
Yes, sir.
It is not. See, heuristically, you can say definitely one term multiplied delta x whole squared. For example, let's take delta x is 0.1, delta x squared will be 0.01. Let's assume that dou squared du by dou x squared is, of the order of 1. It's 1. So it's 1 by 2 into that 0.1, which is 0.05.
Yes, sir.
Second term, dou cube u by dou x cube, let's assume it is 7 or 8. Then 8 by 6 is only 1.2. So it is 1.2 times delta x squared, which is
0.01.
0.01 into 1.2 is 0.012. Correct? So compare 0.012 with the earlier one. Definitely it is of a,
Lesser.
yes.
Yes.
That is how you should understand this order of magnitudes. Okay?
Okay.
You don't, we don't imagine that it will be extremely high. That is, dou cube by dou x cube itself will be thousands and 10,000 times. You don't imagine like that. Imagine that there will be some reasonable numbers, okay, so that you can treat them like a constant, almost same constant.
Okay, sir.
Okay.
Yes, thank you.
So what you asked a very, very pertinent question. There are situations where what you say may be true, but we are looking at a very general case.
Okay, sir.
There may be special points where what you say may be true and the error you commit may be large, but we are just trying to get an idea of how much error you commit. Not the exact error, generally, approximately how much error you will commit. Which error is larger, this one or that one?
Yes, sir.
Main thing is things are not very exactly defined here.
Yes, sir.
You know that, a pumpkin is larger than a orange, but if you compare a very large orange and a very small pumpkin, what can you do?
Yes, sir.
That is unnatural, correct?
Yes, sir. Yes.
So we look at the natural thing. It is possible that the smallest pumpkin may be smaller than a largest orange, but we don't go into that analysis. We say that oranges are, smaller than pumpkins. That's all we say.
Yes, sir.
Okay. Yeah. Okay.
Yes, sir. Understood.
Thank you.
Thank you.
Good. Thank you. Now you go to backward or rearward differential. Okay. We have only 4 minutes left. Anyway, if I finish this, I'll simply say that substitute minus delta x here instead of delta x, and instead of u I plus 1j, you compute it I minus 1j. Here I minus 1 is what? This u of that is x at I comma j minus delta x will give you x at I minus 1 comma j. So instead of delta x for the forward, if you substitute minus delta x, okay, this will become minus whereas delta x whole square will be positive. It will remain as plus. This will become minus. The next term will become positive. Okay. So we can write it as, instead of I plus 1, you put I minus 1 here. It will alternate minus x, minus plus, etc. Now you do the same truncation. You chop off here. Sorry, chop off this here. You want dou e by dou x and solve for that. You will get this solution. Dou e by dou x is e of I comma j minus u at I minus 1 comma j by delta x. Plus truncation order is same, first order, error. Now you look at this expression and compare it with this expression for forward differencing. They will be very similar. Okay. Truncation error order is same for both are first order. One, you take the current point and the next point, forward differencing. You predict the next point by the current point. In the other one, you make use of the current point or the previous point. Why do you make use of these points? For the same reason, to calculate dou u by dou x. Okay. So what I am finally getting is an expression for dou u by dou x through forward differencing is given in the last line of the slide. Through backward differencing is given in the last line of this slide. In both cases, we are computing only dou e by dou x. Which way is correct? We don't say this is correct or that is correct. These are two different ways of evaluating this dou e by dou x. Okay, so we'll stop here now. We'll move forward tomorrow. Take attendance. Okay. Any doubts, or shall I end the meeting? Any doubts? Sanjay, shall we end the meeting?
Oh, sir. Yes. Thank you, sir. Bye.
Thank you. Thank you. Bye.
Thank you.